Hi, I'm Miss Hearn. Let's get started. And if you find this video helpful, please remember to give it a thumbs up. That helps other students to find the video. Okay, so we had said that the limit of the difference quotient is the slope of the tangent line to the function f at the point x sub 0. And now we're going to give it a different name. We're going to call that the derivative of the function f at the point x sub 0. Those are synonymous. They mean exactly the same thing. We're also going to introduce a shorthand notation. You know we love shorthand notations. We're basically lazy. So instead of writing the limit of the difference quotient every time, we're going to write f prime, f with a little apostrophe, at x sub 0. So once again, we interpret the difference quotient as the slope of a secant line. The derivative is the slope of a tangent line. We can also interpret the difference quotient as an average rate of change, like an average speed or an average increase in profits over a time interval. And the derivative, the limit of the difference quotient, we call the instantaneous rate of change. That's the speed on your speedometer at a particular moment in time. So the vocabulary is going to be really important because when you read a question, you need to know if they're asking you for just the difference quotients, just the slope between 2 points, or are they asking you for the limit of the difference quotient? Those are the two possibilities. So let's look at this example. Changing volume of a ball. What's the rate of change of the volume of a ball with respect to the radius at the moment that the radius is equal to 2? Okay, so to visualize this, we have a ball and maybe we're pumping it full of air or something. Something is causing this ball to expand. The ball is a sphere with a radius r. And at one moment in time, the ball looks like this. At the next moment in time, the ball has expanded and it's larger or smaller, whatever the case may be, shrinking or growing. Okay, so maybe this was at when the radius was r sub 0. We often use a subscript 0 to indicate a particular value as opposed to the variable value r. And then maybe this is r sub 0 plus h. There's been a little bit of change in the radius. Okay, now in this question, they're asking us at what rate the size of the radius, or rather, at what rate the volume of the radius, volume of the ball is changing when the radius is actually equal to 2. So it's not, for example, saying what's the average rate of change of the volume between when r is 2 and when r is 3. That would be a difference quotient, a slope formula. We'd have 2 points and 2 values to use, and we could just find a regular slope calculation. This is at a particular value of r. Think of it as at one moment in time. We're talking about a limit. So if we're looking at one moment or one value, we're looking at the instantaneous rate of change. And you know this because it's one value. If it was 2 values, we'd be looking at average rate of change. So that tells you that you're taking not just the difference quotient, which is a slope formula, but the limit of the difference quotient. The limit of the difference quotient, written in terms of f's and x's, was the limit as h approaches 0 of f of x sub 0 plus h minus f of x sub 0 divided by h. We're talking about v's and r's. Think of the volume as being a function of r. Volume at radius r is 4/3 pi r cubed. So putting the limit of the difference quotient into that notation, you still have the limit as h goes to 0. You have v of r sub 0 plus h minus v of r sub 0 divided by h. Now, what is the r sub 0 in this case? 2, that's right. We want to know at that moment when the radius is 2, what exactly was the rate of change of the volume of the ball? So we're going to take the limit as h goes to 0 of v of 2 plus h minus v of 2 divided by h. So we're going to need to plug into the volume formula. So we have the limit as h goes to 0. And the volume formula is 4/3 pi r cubed. So we're going to have 4/3 pi times 2 plus h cubed minus 4/3 pi times 2 cubed divided by h. Okay, now just to make this a little easier to look at, remember that we can factor that 4/3 pi in the numerator. We can factor that out. We can actually bring it through the limit because of our limit laws. You don't have to do that, but I think it'll make it a little easier to deal with. So we're going to put 4/3 pi out front. Limit as h goes to 0. And we have 2 plus h cubed minus 2 cubed divided by h. Okay, now be careful with your algebra here. 2 plus h cubed is not 2 cubed plus h cubed, right? What do we have to do there? 2 plus h times 2 plus h times 2 plus h. So that's right, Merlandi, expand it out. So we're going to have 4 plus 4h plus h squared, and we have to multiply that times 2 plus h. So it's going to be 8 plus 8h plus 2h squared. I multiplied everything by the 2. Plus, we're going to have 4h plus 4h squared plus h cubed, multiplying everything by h. Okay, so what does that turn out to be? 8 plus 12h plus 6h squared plus h cubed. So we're going to have 4/3 pi limit as h goes to 0 of 8 plus 12h plus 6h squared plus h cubed minus 8 divided by h. And with polynomial functions, it should always be the case that in the numerator, any terms that don't have an h should cancel out if we did our algebra correctly. So that means we have 4/3 pi limit as h goes to 0 of, dividing each term by h, we have 12 plus 6h plus h squared. Okay, so now we can plug in the 0. So we're going to have 4/3 pi times just 12. So that's going to be 16 pi. If you found this video helpful, please give it a thumbs up. That will help other students to find the video.